Hello, I'm Brendan Smart, and I'm here to present Bootstrapping the Relationship Between Images and Their Clean and Noisy Labels, which was authored by myself and Gustavo Carneiro. In this work, we aim to address the noisy label learning problem, where we wish to learn from datasets with incorrect or corrupted labels. We focus our work on instance-dependent label noise, where the true labels and image features affect how a sample is likely to be mislabeled. Many of the state-of-the-art approaches in this area, such as divide mix, discard noisy labels after relabeling incorrect samples. However, this limits our ability to learn the joint relationship between image features, noisy labels, and clean labels, which could potentially be used to relabel other noisy samples in our dataset. Other methods do attempt to directly learn this relationship, using a model like the one on the right to predict clean labels from images and noisy labels. However, these methods require a subset of training data with clean and noisy labels, which can be expensive or infeasible. Furthermore, these methods require distillation to a more standard model, like the one on the left, before they can be used for evaluation on samples without noisy labels. In our paper, we train a model, like the one on the right, using a new training algorithm that discovers and utilizes the relationship between image features, noisy labels, and clean labels without requiring a clean subset of data, and that can classify images with and without noisy labels. To do this, we first aim to find a small, representative subset of samples whose labels we are confident in. We first perform self-supervised training with SimClear to learn a good feature representation without overfitting to the noisy labels, and then perform a small amount of supervised training with early stopping. Our model is then used to predict the label of all the samples in our dataset, averaging our predictions across multiple weak augmentations of each sample. We then select the samples we are most confident in from each noise transition, using an estimated noise transition matrix to balance our selection. Now we have a small subset of our data with images, noisy labels, and estimated clean labels. These samples can be used to bootstrap a learned relationship between images, noisy labels, and clean labels, which we can use to relabel the other samples in our dataset with higher accuracy. Here we use a modified implementation of fixed match, directly supervising our clean set and using consistency loss on the noisy samples. During this stage, we also randomly replace the one-hot noisy labels with zero vectors, training our model to predict with and without noisy labels. Finally, we relabel all the remaining samples and complete one final round of supervised training. Here we see that our method is able to achieve state-of-the-art results on Web Vision and Animal 10N, showing the utility of using noisy labels to aid relabeling. Interestingly, we also find that by applying augmentation at test time, we can meaningfully improve results even further. We find that we also achieve state-of-the-art on the common synthetic asymmetric benchmark on CIFAR10 because of the strong relationship between noisy labels and true labels. However, our results simply match other methods on symmetric noise because symmetric mislabelings don't meaningfully relate to image features or noisy labels. Finally, a unique feature of our method is that our final model can be used to predict the labels of samples with and without noisy labels. Here, we show how our model changes its predictions when given different noisy labels for a test sample, showing that it has learned to make the correct prediction without a noisy label and on classes which are commonly labelled as dog in this dataset. Importantly though, it has also learned to make other predictions when provided noisy labels for classes which are never confused with dogs. If we have access to noisy labels for all testing samples, as is the case in tasks such as tagged image classification, we are able to utilize this to make more accurate predictions. Thank you for listening.